Thank you very much for the introduction, and also thank you to Professor Yalçınkaya for inviting me. I want to take this opportunity to talk about our work on twinning. You know, we're trying to understand the fundamental issues in modeling of twinning, and I think it's relevant to this conference because I noticed that a lot of people are working on crystal plasticity. And I want to specifically talk about various things related to twinning, including shuffles, offsets, disconnections, sharp boundaries, minimum energy paths, critical resolve shear stress, and its elevation. And these are the three students I have currently working on twinning, Samir, Orçun, and Görkem. And I had also former PhD students who worked on twinning, İbrahim Karaman, Demircan, Jana Dinç, Reggie Hamilton, Sandip Kibe, Tawhid Ezaz, Piyash Chowdhury, Avinash Osha, Sertan Alkan, and Yanvu. So mainly I'm going to talk about newer things, but I want to give a little bit of historic background as well. First, I would like to speak about the twin nucleation in face-centered cubic materials, because this is the easiest case to see. And then I'm going to talk about more complicated lattices like B19 prime, which is a monoclinic lattice, B2, which is an ordered cubic lattice, and then I'm going to talk about twin slip interactions, okay, which result in critical resolve shear stress elevation, increase of critical resolve shear stress. In particular, the latest work we are doing is understanding the evolving dislocation cores when we have twin slip interaction. Going back to the face-centered cubic case, we have the original work was done in the mid-2000s with Kibe, and I want to talk a little bit about that at first. Before that, I just wanted to mention that the stress-strain behavior of pure medium to high stacking fault energy materials, metals, display stage 1, stage 2, and stage 3. This is typically stage 1 is single slip, stage 2 is multi-slip, and then there is cross-slip onset at this point, and then you get decrease in the strain hardening. Now, in materials with low stacking fault energy, you do get stage 1, stage 2, which involves slip mostly. But at some point, when the stresses reach a critical level, twinning starts, and then one could get twin slip interactions, also twin-twin interactions, which initially may appear like a bit of maybe softening or localization, but then there could be substantial hardening associated. This is again for pure materials, pure metals with low stacking fault energy. Now, if you look at low stacking fault energy alloys, they already have a fairly high friction stress, so they might start to twin right at the onset of loading, in other words, at fairly small strains, and the twinning starts here, and we get this upward curvature in the stress strain curve. That's typical of these Hatfield steels, iron manganese steels, as well as nitrogen steels, and also high entropy alloys, medium to high entropy alloys display this kind of behavior. So these are some photographs of, this is twin-twin interaction here, and showing here, again, obviously in face-centered cubic material, twinning is on 1-1-1 planes, right? And then And, you know, we have a number of works published, but nowadays there is some interest in high entropy alloys. So we do discuss this in this particular paper that was published in 2018. If we look at the earlier work, that was, this is how the dislocation structure looks like in low stacking fault energy materials, basically planar dislocations. And then if you have twins here, you see there's twins here, and then there's slip here as well. So there's twin slip interaction. We just discussed that here. And the classical description of twinning prediction, twinning stress prediction is goes back in 1960s. It's more or less an empirical equation. Tau critical scales with gamma ISF, which is the intrinsic stacking fault energy of the material. And the higher the intrinsic stacking fault, the twinning stress increases. But in this description, there are a number of fitting parameters. And so it requires fitting, and this is like a semi-empirical model. So we want to understand the twinning better. Of course, this is for face-centered cubic copper-based alloys. Now, we need, as I said, we need a more fundamental approach. So this is the picture of twinning. Twinning is, of course, a mechanism of plastic deformation, and it's like an abrupt reorientation of the crystal, right? And so this is the matrix, this is untwinned, and this is the twin region here, okay? And it looks like this at the micro scale. This is the twin region. This is region that has some micro twins also, but it has matrix which is undergoing slip. That's Hatfield steel. And of course, the stacking of the atoms such that in face-centered cubic, you have typically ABC stacking. And here you could see the mirror symmetry across this lower twin boundary. So it's C here, layer. This is 111 direction, 111 direction, 111 plane, 112 direction is the twinning direction. And this is the upper twin boundary. Again, there is a mirror symmetry across the boundary. And the way that gamma ISF is determined is by shearing of the atoms in 111 plane and 112 direction. You go through gamma unstable stacking fault energy, then there's a metastable equilibrium point, which is the intrinsic stacking fault energy. That is if we deform in the 112 direction, shear in the 112 direction. If we shear in the 110 direction in face-centered cubic materials, this is again all in the 111 plane, but in the 110 direction, excuse me, 110 direction, the barrier is higher. So the material prefers to split into partial dislocations, which are the 112 dislocations here, and go or deform through 112 direction. So this is the 112 here, and that's the one. So that's like the zigzag pattern of plastic deformation. This will be the 110 direction. So that the area under this curve, of course, energy for stacking fault formation during passage of these Shockley partial, it would be the area, in this case, really the area under this curve here, shown here. The way these curves are obtained, you first you have the ABC stacking, 111 plane, 112 direction. You displace the you displace B in the 112 direction as shown here, and then you displace the next plane, and you get a single plane here. This is the intrinsic stacking fault. Actually, here the B is our fault plane, and we're displacing the next plane here. And then if we displace the the following plane and by a fraction of the Berger's vector, we get this B to move to the C position, so that we get a two-layer fault, and then we subsequently shear the following layer, and then we get a three-layer twin. So it is a successive shearing of the planes and produces this energy barrier. First one is gamma US. The second peak is gamma UT. That's the unstable twinning fault energy. And this is the 2 gamma 2 TSF. That's twinning stacking fault energy because there are 2 planes here. So this is gamma is millijoules per meter squared. UX is displacement in the 112 direction, which is shown in here. So one notes that in the phase canted cubic, it's successive displacements along the 112 direction. And often the initial peak is associated with, or the initial formation of the first 2 layers is or in fact the 3 layers is the nucleation of the twin, and then the subsequent growth is the migration barrier after the 3rd layer. So we first developed these numbers, gamma US, gamma ISF, and gamma UT. And of course, we cannot measure experimentally gamma US or gamma UT, but one can measure gamma ISF and also the gamma TSF. And these theories is from, this is a long time back, some of the earlier density functional theory calculations for these barriers, and they match the experiments reasonably well. And then, of course, we want to determine the twinning stress. We have dislocations bounding the twin here. And so there is the edge and screw components. These are the dislocation energies, strain energies associated with dislocations. This is work done by the applied stress. And GPFE is the energy associated with the twin energy pathway. That's the integral of the energy paths that we discussed here. So we write the total expression, and then we minimize this expression and with respect to D, which is the width of the twin and the number of layers. And we get a twinning stress expression, which is a function of gamma UT, 2 gamma TSF, gamma ISF, the twin Berger's vector for the twinning, which is related to the lattice constant, of course. And we find that doing that, we are able to predict, when we plot our prediction of critical stress versus gamma ISF, this is silver, this is gold, this is lead, this is copper. Nickel is pretty high in terms of twinning stress. But we immediately note that any expression that simplifies the critical stress with gamma ISF, whether we take linearly or square root of it is not valid, is a better correlation with gamma UT. And that's what basically came out of this work in 2007. I mean, we've come a long way since then, of course, but I just wanted to give you an idea of how we approached twinning stress determination. So these are our calculations, and these are the experiments. There's a scatter in the experimental results, and there's a reason for that. But these experiments, the ideal stress, twinning stress, is taken from the slope of these energy curves, and that gives you a huge number. That's ideal stress, and not involving any presence of any defects. So I want to say a few things about more complicated structures, and this is more recent work, 2020, Samir. We discussed so far on the face-centered cubic twin, and that's a very simple case. That's also called a compound twin. But So the common perception of twin boundary is face-centered cubic, like in copper, okay? But the interface structure is very clear here, right? And we shear the atoms, like I showed there earlier, and we just get it. But what happens is in these crystals with lower symmetry, we get irrational twinning planes. So this plane here, which is the twinning plane, so this is a twinned martensite or twinned B19 prime, is not a flat plane. It has some regions which are high index planes, like 111, but there are these ledges. So the resultant plane is actually something like it's irrational. The twin boundary structure is not clear. There are some experimental observations of this, such as this, and by others, but we wanted to understand this structure. So this is nickel titanium. If I didn't say it, yes, right there. This is nickel titanium B19 prime. And we want to predict the twinning stress, of course, in this material as well. The complication comes out like this. So if we have, this is the ABC, and there's an angle here, you know, not 90 degrees, that's the monoclinic lattice. And then if we look at the twin here, one way to visualize the twin is 180-degree rotation along the 011 direction here. So go back here and then say that this 180-degree rotation is supposed to put the atoms in a reflective position, but it does not. It does it in face-centered cubic, but not in the lower symmetry lattices. First of all, we have to consider offsets here at the interface. So this is x0. So the two twin variants, you know, lower part and the upper part of the twin. This is the twin boundary, right? Has to have these offsets, because these offsets actually are necessary to get a minimum twin boundary energy. Otherwise, the twin boundary energy would be extremely much higher. So we calculate these offsets, x0, y0, and z0, before we first have to construct the twin boundary correctly. And that's what we're doing in the, before we engage in any calculations. And as I mentioned before, there's another complication in this case. Because there is a misfit between these two variants, these ledges have disconnections. So those are dislocations with step character. So these are called disconnections, and we calculate the spacing of these ledges or these disconnections at these boundaries. This is a competition between misfit energy and strain energy. If D is too large, then the strain energy becomes very high. But if these disconnections are spaced too frequently, then the misfit energy goes up. So there is a equilibrium separation of these disconnections. So twin partial build up, twin partial separation. So this is how a twin advances. These ledges are moving, so that, and it's more complicated than what I'm showing here, but this is how the orange, the top part here, overtakes the bottom part of the variant. So this is variant A, variant B. So it's an internally twin structure in martensite. And this is so the important thing to note is that this is the twin variant here, M1, M2, and that's the martensite. And then we find experimentally that slip emanates from these twin boundaries too. So that's another important observation. And so there's the twinning, and then there's the slip emitted from the twin boundaries in these materials. And emitted slip system agrees with the twinning direction and twin plane. So so essentially, this is the mechanism of slip formation in transforming alloys. It's applicable, of course, to other materials, not only nickel titanium, but also to other conventional materials like trip steels, etc., with some differences, of course. But again, what we're showing here is how the slip emits from this. This is the twin boundary. This is the twin boundary. This is martensite. This is austenite, and the slip emits from these twinning dislocations at the boundary. This is a schematic. Of course, we have a simulation of this as well. And I think the problem gets a bit more complicated. That's the twinning motion. And then if there is some sort of a hindrance to the twinning motion, when we unload, partially it reverses, but then there's a reaction here and the slip is emitted. So this is the austenite, this is the martensite. So there's some reversibility, but not full reversibility because because of the internal misfit at the boundary. Now, I just want to mention that everything I talked about there is type 2 twin boundary. So in these materials, you could get higher order twins. These are developing at higher stresses. So this is 001 plane, this is 201, this is 113 twin. So, different twin planes can be activated. We discussed this in this paper and in other papers too. We look at different materials. These are nickel titanium, nickel manganese gallium, cobalt, nickel aluminum, nickel. So we show the experimental results with blue, and we try to predict this twinning stress. And the results are shown there. Again, things get a bit complicated because again we think of twinning as a reflective boundary, twin boundary here, but when we look at 114 plane in B2, this B2 means order cubic. Again, this is nickel titanium, this is austenite. We have to have shuffles to get this reflective boundary. So in other words, there's the shearing, but there's also the shuffling. This eta is the shuffling. And so when we look at the minimum energy path, it involves both shear and the shuffle. And that is the path that it will take to go through the minimum energy peak. So the material prefers to go along there. So that's 112 twinning plane. If we look at the 114 twinning plane, now the path is shown here. It's a complicated path, but again, it avoids the large peaks here. And the peak actually we get is about 148 millijoules per meter square, which is not very high. These peaks are extremely high. And this is also published, of course. This is the other complication, excuse me, is this what's called this sharp boundary here. You see, this would be a reflective boundary, but if this atom that's supposed to be here, stays there, the energy is higher. So if this atom is displaced slightly, so there is a little boundary shift, that gives you a lower energy. So sometimes these at the twin boundaries, the position of the atoms can be different than expected, and this produces a smaller energy barrier. So if we did calculations with the traditional FCC kind of thinking, we may be off, and I'll show you that. So we're doing this is the current work we're doing now, just going to appear in the next couple of weeks, I think, in the Acta Materialia. And the twin boundary in titanium or HCP materials is pretty complicated. It has a corrugated structure like this, right? So, and this is, you know, based on lattice considerations, this is how it looks. But what we found is that there has to be some initial offsets to minimize this twin boundary energy. The boundary energy here with this corrugated structure is quite high. So what we did was and this is the work with Samir and Görkem, no common plane. It's not clear where the twinning plane is, you know. It could be here, it could be here, you know, it could be, so the twin boundary structure is not known. What we found is that to minimize the energies, we need to offset the atoms by a certain amount. And again, we have typically these offsets at the boundaries to preserve the lattice spacing across the twin. So the traditional view that we find in textbook, this corrugated structure, doesn't preserve the lattice spacing, which should be 1.73. But if we do the lattice offsets, we minimize the strains, and we get the correct twin boundary energy, because this energy associated with this and this structure is different by 60 millijoules per meter square. Again, the motion here is a bit like similar to nickel titanium in that regard, in the sense that it has a disconnection, and this is these are the shuffles involved, so it's a little complicated. We do have a calculation of the minimum energy path. This is a nudge elastic band calculation, and that's the barrier. So the barrier is not that high in our calculations, but this so it's a good sign. But just to show you this let's do this again. Sorry about that. You see the disconnection motion here. You see that's the step here. It's a periodic boundary condition here. This is just to illustrate the movie. So the other twin systems are possible in HCP, but they all involve shears and shuffles. So it's a bit, this is 112, 1 twin, 101, 3 twin. So the twinning in HCP system is actually a bit complicated. Going back to our original twin, we calculated these barriers again for magnesium, which is down here, titanium, which is here, this gamma UT, gamma TSF here, and hafnium, and zinc, and cadmium. And the same ideas, the gamma UT, and then this migration. Part one. We presented a hierarchical multi-scale adjustable parameter-free approach for twin nucleation FCC metals and alloys. We are saying that shear, shuffle, and disconnection must be accounted for in describing twinning. So I would like to say a few things about BCC. The BCC is also a bit complicated. So we have slip nucleation, twin nucleation, and twin migration. So there are three kind of parameters. And the migration is same idea to get the energies, the And this happens to be iron chromium, gamma US, gamma UT, etc. And we did predict these are ideal values, too high, of course, but experimental values for iron chromium, these are all BCC. A better model is needed. And the way that the dislocations are, we don't have partial dislocations in BCC, we have fractional dislocations. So this is 111 screw dislocation, but it's split on 3 planes. And the way the twinning happens is that this dislocation has to come here, this fractional dislocation has to come here, and then they form this 3-layer nucleus, and then we need to, again, do a kind of a similar consideration, consider the interaction energy of these partials, work done, and then we have the GPFE. And if we do that, I don't want to go into the details, the critical stress against some gamma parameter, the twin boundary migration energy, we could see that iron alloys can be predicted, the critical stress for twin nucleation here. So the experimental was here, and this is published, by the way. Did I point that out where it's published? I apologize, but I will in a second. There is reasonably close agreement here. And we looked at other various materials like niobium, tantalum, etc., vanadium, and we're this was done in 2014 with Avinash in BCC metals and alloys, again twinning. So the summary twinning stress calculated based on a Piaz-Navarro formulation and GPFE curves provides a good basis for theoretical study. So far, I've talked about pure nucleation and migration. I didn't talk about what happens when you have both slip and twin, right? That's become very interesting. So there's a dislocation reaction here, and we get a residual Burgers vector here. And this is residual Burgers vector, and then those partial migrates and increases the twinning by an atomic layer. So this is the scenario that we have. Twin migration stress is the stress required to move the twinning dislocation along the twin boundary. What happens here is quite complicated, I would say. One can do a molecular dynamics simulation, yes, if we have the right potentials for very pure metals. But there are so many possibilities, so many reactions, right? So the residual there is B1 is the incoming dislocation, and the B2 is the outgoing, and then the residual is what's left at the boundary. And we can determine the direction of that dislocation. That the Burgers vector has to be conserved, but we don't know the plane. And that's what we're working on. And initially, we did the calculation similar, looking at the total energy of the system and minimizing it to get an idea of the migration stress, which would be this stress, steady state migration stress, apologize, here. And, we said that migration stress is lower than the nucleation stress, right? So these numbers are below 1. So these are our experiments with chromium, we did iron chromium alloys. And it's in reasonable agreement. This is at small strains. When we go to larger strains, there are more complications. We have twin-twin interactions. This is on high entropy alloys. And so there's the critical stress for nucleation, twin nucleation. This is twin migration stress, and then this is twin-twin interaction, where we have self-hardening, hardening of the primary. Well, in this case, this is the primary system, the green one, and then there's secondary system. And so there's both self and latent hardening. So that latent hardening gives you this, because of this interaction, gives you this additional hardening. And we try to determine these. So if we look at the critical stress that evolves with gamma dot on the slip systems, there are twin systems as well, 12. There are potentially 12 systems, but in reality, there could be only 3 or 4 in these cases. And we are trying to determine this latent hardening matrix here, right? So this is generally is assumed. There's a formula that's suggested a long time ago, a good formula, but it's only applicable really to phase-centered cubic materials, and people tend to use it for various materials, including BCC, et cetera, but it depends on the very specifics of the interaction. So we determine this H alpha beta matrix in this case, and we can get the hardening slope, predict the hardening slope, and the experimental slopes are here. This is the slope of the stress strain curve. I should point out a lot of our experiments are single crystals, so single crystals, because that's how we determine how our model is, and that's how. So overall hardening, we are able to predict, and including polycrystal, and then 111, 122. This is strain hardening, and this is as a function of strain. So we're showing our predictions in comparison with the experiments. Now, at this point, we should point out that when we have these multiple systems interacting, initial onset of yield can obey Schmidt law, of course, but subsequent flow does not satisfy Schmidt law, because it depends on the reactions, and it depends on the stress state component. So the classical description, tau critical, is equal to some characteristic number. But S11, S22, S12 are the other stress components, which are non-Schmidt components. So we determine these numbers. And this is mostly the work that Sertan Alkan did a 3 years ago. And we are obtaining these generalized yield criteria now almost. It's the case with BCC, of course, because we already know there are fractional dislocations on multiple planes. So the stress state is not dictated by a single plane; it's dictated by the shear on other systems, right? But also normal stresses have an effect. So we said to ourselves in the last year, with Samir and Orchun, we said that, what are the, we cannot run molecular dynamics for each cases. I'm almost finishing. We cannot run MD simulations. And in fact, for these high entropy alloys, it's virtually impossible to find reliable potentials at this time. So we said, can we do these in an incorporated methodology to account for all these reactions and everything? So there are 19 possible reactions. This is incoming dislocation. This is a twin plane here. You see there's a reaction there and incorporation, and then there's slip penetration through the twin. So we are developing another model, a more comprehensive model to take. So this is the PR stress. This is, I didn't talk about that in detail. There's an image stress, of course, between when the slip approaches the twin. So there's elastic energy, misfit energy, image stress, and then applied work. And we're trying to, this is the core width of the dislocations. So this is an incorporation reaction. There's a stair rod here. That's the residual dislocation here. So there are a lot of parameters. There is the core width of this dislocation. There's the gamma UT, gamma US appearing. There's core width of this one, core width of the incoming, which are all unknown. Because when they are interacting, core widths are evolving. It's not a fixed core width. Like we can't say it's lattice constant divided by this much. That's what we're trying to determine now. And we point out also that when that slip comes in there, that residual actually is split on two planes. So here that's the two planes. So we're determined, you see, and this is the dislocation density distribution for the this Piaz-Navarro dislocation. So there's a density distribution here. The core width is here, like here. And so the core widths are different and they're evolving also. What we're trying to determine is that initially the stresses are high at the interface when there's this reaction, but then when the incorporation occurs, the stresses go down. So that's the peak stress we think that affects the strengthening in high entropy alloys. We did some simulations and to check the model for simple cases, like that peak stress I mentioned is the twin interaction. We checked it for lead, silver, copper, depending on, this is all our new analytical model. And for iron-based high entropy alloy, well, FCC high entropy alloy, depending on the reaction, we can get these numbers like 140, etc., megapascal tau. They are in reasonable agreement with experiments. At this point, it's important to point out that these stress levels, that peak stress levels, the interaction stress levels, depending on the residual Berger's vector. And that's borne out by these experiments, this hardening happening here again. We are seeing that. So this is the sliptwin interaction cases. I would say that twinning stress upon twin slip interactions are rather complex and results in considerable CRSS elevation. The trends in FCC and BCC always differ. Migration in FCC undergoes CRSS elevation. That's what we're showing in these high entropy alloys. Recent work, steroid is partitioned to multiple planes. Thank you very much. And sorry, I ran a little out of time.
That was great. Thank you so much. Very impressive overview of twinning on so many material systems, and very impressive.
Thank you.
So the floor is open for discussion now. Any questions? If you could raise your hand or unmute yourselves. Oh, that's clapping. Am I missing? There's too many people here. Can I start otherwise? Oh, there's a question here. Oh, that's Tunka. You can go ahead and unmute yourself.
Yeah. So I have a question in the context of crystal plasticity simulations. Many of the people disregard twinning. I mean, they don't take into account at all, even though it is relevant in certain materials. How would you comment on that?
You know, I think it's a really good question. When we're dealing with hexagonal close-packed materials, and they are now extremely popular, like magnesium, titanium, these materials, as you know, do not have sufficient number of systems to satisfy the Mises criteria. So twinning is definitely an inevitable mechanism of deformation in these materials. That's my view. At low temperatures, definitely in a phase centrifugic and body centrifuge, it's a dominant mechanism. At high strain rates, it's a dominant mechanism. I would say that for very high stacking fault energy materials at room temperature, quasi-static loading, like in copper or aluminum, in laboratory experiments, we don't see that much twinning, right? Mm-hmm. But in almost all these phase transformations, like trip steels, TWIP steels, TWIP, TWIP, mm-hmm. TRIP, TRIP, high entropy alloys, there is amazing amount of twinning.
Mm.
In high entropy, all the stacking fault energies are extremely low. Yeah, not all, but most of them are very low, like in those. So twinning is going to happen, maybe not immediately, but after a few percent. That's what we're seeing, right? So what do I think about it? Well, I think it's an evolution, right? You know, people, I think the more we discuss it, the more we teach about it, I think people will incorporate it in their crystal path, maybe in a simple way at first, but it should be there.
It's a very complicated microstructural phenomenon, actually, but it could easily be incorporated by, I don't know, increasing the critical result shear stress, etc. There could be some phenomenological way to include. Yeah. Okay. Thanks.
Sure. With some interaction term.
Yeah.
Definitely. I mean, in a simple way, it can be done. Yes.
Thanks.
Thank you.
If there are no other questions, I may ask something myself. So I'm not an expert on this field by any means, but I have actually two short questions, if I may. So one is in relation to the comment you made, because I've seen quite a lot of work on MD in high entropy alloys, but you seem to be a bit skeptical about it. Is that correct? Is my interpretation correct about it?
You know, like everything else, MD is a very nice, powerful tool, but it's easy to learn it. You know, we teach it now, you know, in our graduate courses, right? Even in a plasticity course, we're covering it. But it works great for pure metals. But when we have multiple elements, some of these elements segregate to the faults, to these like stacking faults. So in our case, the cobalt prefers to segregate there. So one has to look at where the positioning of the atoms are, and these kind of things. The calculations we made are often with the electronic structure codes, which are the density functional theory codes, because those are not requiring to have MD potentials. So with some, you know, thinking and consideration, understanding the limitations, I think MD can be used for alloys, and people are trying to do that as well, I think.
Okay, thank you. And maybe just very briefly, it was very interesting what you were presenting on the HCP, and I was wondering if you could elaborate a bit more. I'm not sure if we have much time, but about I would say the interplay between the spacing and the corrugated structure. I thought it was quite interesting what you found in there.
Well, that was a surprise to us to do the HCP work, because you know, there's been a lot of interest in magnesium and these light alloys, and so the twin boundary structure we found is certainly the correct one, and I think one can perhaps get it accidentally too if you do the right relaxation in an MD or something like that, but you may not be aware of that it's happening. MD is actually doing that. So we did it systematically. So it was a lot of the pictures that are in papers and in books show this zigzag pattern, but actual pattern is not that. There's a shuffling there, and so it's the boundary has a minimized energy or minimized strain as well, and the correct spacing across. This paper will probably be appearing in a couple of weeks as a, you know, in ACTA.
Excellent. Thank you. I look forward to reading it. Yeah. Very interesting.